So, I have a quiz for today. We'll get up to that eventually. That's a multiplication on the first problem. I just separated them so that it wouldn't look like a cube root. It looks real complex, but it shouldn't be, right? You just got to set it up in that log form that we did. You convert all those things to fraction powers instead of roots. Well, I was hoping everybody would be here. We need to figure out when to do the next test. Right? I know auditors are trying to catch up on 2. I know you're still trying to catch up on 2. But what we were going to go over today, or what we probably still will at least go over a little bit, was going to essentially be the end of what's on the third test. So we kind of did that really, really quick. But when there's only a few of us, it's really easy to go through it quick, especially if you get it. If you struggle with it, it takes a little bit longer. So what's today? Today's the 20-something? Yeah, so 23rd. Well, we can still have the test on the 7th. No, it'll be on the 2nd. What's 2 weeks? What's a week from Thursday or Wednesday? A week from Wednesday. Oh, it's April 1st. Yeah. So we'll take the test on April Fool's Day. That sounds like a plan. That way, today we can finish up this. If on Wednesday we'll probably have to go back through this because we're missing half the class, and then the following Monday we'll do a review, and that'll give us time. Hopefully, that still gives us a month to do the last chapter and finish a little early this year. Stuff to do. Okay, so let's see. Since you guys are the only 2 here, we should kind of go back over some of this stuff. So far for this test, right? We did implicit differentiation with the x's and y's, dealing with those derivatives. Let's see, we did derivatives of log functions. We also did universal trig functions. Oh, we did the song. And we did And then we did the very last thing last time where we just talked about approximating the square root using that formula. Now, either of you guys have any questions about this stuff for now? Because we can go back over, I can go over anything about this stuff. Don't question. It'll save us from spending too much time on the other stuff that it'll save us from spending too much time on the other stuff that I'll have to redo anyway, because it's probably the hardest thing that's going to be on the test. That's the last thing we were going to go over today. Questions about this? You guys okay? On this? That was just those formulas, right? So you had the sine minus 1 of 7x squared, and you were looking for the derivative, right? It's very similar to the quiz, to where you have, if this is the function, then the derivative was 1 over the square root of 1 minus u squared of du. I think that's the formula. Yeah, that's it.
And that's logarithmic differentiation instead of smooth.
Well, yeah. So where you take it and break it apart. So like the one you have in the quiz, right? It would be, and I'm just going to write something close to it. I don't remember what it was. Something like that, right? And so you would want to first rewrite it as everything raised to a power. Right, and then you would use those log rules. Right, so the numerator is positive, denominator is negative, and all the powers just become all the exponents just become constants. Right, so when we take the natural log of the whole thing, we get the natural log of x squared plus the natural log of 3x squared minus 7 minus up to the 1/2 8x squared minus 12 to 1/3. And then we just make all the exponents, and use the power rule. And then you take the derivative, or just on that quiz, you're not going to have enough space to write it. You have to write it on another page. There's a lot of problems take a little bit of space. Not necessarily a lot of work, but just a little bit of space. Okay. So let's see. The last thing that goes on this test that we haven't talked about, section 10 in chapter 3. So the last thing that's in this chapter that's going to be on this test is probably it's one of the more useful things in calculus, right? One of the things that we can actually use to explain real life things as opposed to just finding derivatives of functions. It basically just takes and relates the rate of change of one variable to another, right? So we've got some formula that's going to describe how these things are related to each other. And then we're going to use how one variable changes to determine how the other variable is going to change. So for example, think about blowing up a balloon. Right? You can determine the volume of the balloon based on the, assume it's a spherical balloon, because that makes it easier to understand. Well, the volume of a sphere is given by 4/3 pi r cubed. And so the volume inside that spherical balloon, or any kind of, you call it a basketball, even if you think of it like that. The volume inside there is going to be entirely dependent upon the radius of the ball itself, right? And so as you're inflating it, the radius is going to change. And as the radius changes, the volume changes. And so as this ball gets bigger, the radius gets bigger, and so the volume gets bigger. Right? So there's the two variables that are related to each other, and if we know how one of them changes, we can determine how the other one's going to change. And that's the whole idea of related rates. Just trying to determine how one changes with the other. So we're going to start off with a really, really simple example, and then we're going to work our way up into harder examples, and then we'll work our way into examples that actually are meaningful. It's one of my favorites too. So let's see. And look, you guys, not that it's going to help you out out here, but I'm recording this entire thing, right? So you can go back and play this back. That's what I was setting up just a minute ago. Whenever I upload it to Canvas. So instead of uploading notes, I'm going to upload a video. And that way I can upload the notes too if you want. But that way you can kind of go through, listen to it again, and the folks who aren't here can go listen to what I have to say this time. Then we'll probably go back over it. So we want to know how does the circumference of a circle change if the radius is changing by 2 centimeters per second. That's all we know is how fast the radius is changing. But that's all we really need to know. So the circumference of a circle, right? The circumference is just the distance around, is equal to 2 pi times the radius. That's our formula. That's going to essentially connect these two variables. Connects the radius to the circumference. And so we want to know how the circumference changes. Well, we want to find a rate of change change of circumference over time, then we need to determine dc over dt, right? The change in the circumference over the change in time. That's just what this implies here. And so to do that, we're going to take our formula, and we're going to use the ideas that we used when we did implicit differentiation. And so now, just instead of x and y, our variables are just c and r. But we're still going to treat them just like we did when we took the implicit derivatives. Right? So the derivative of c is just going to be 1 times dc. And 2 pi is just a constant, so it just stays there. And the derivative of r is just going to be 1 times dr. So now, we have dc is equal to 2 pi times dr. Right? We just kind of ignore the 1s. Then remember, we can divide both sides of an equation by the same thing and never change it. Right? So essentially, just divide by dt. And now we can see that we have the rate of change of the circumference, dc over dt, that thing we were looking for. We can find that rate of change based on the rate of change of the radius. Well, dr over dt, that's what we were given in the problem. And that was just 2 centimeters per second. It's going to find the rate of change of the circumference. It's going to be 2 pi times 2 centimeters per second, which is 4 pi. Got What's 4 pi as a decimal? 12.7? 12.4? Thank you. So if the radius is changing at 2 centimeters per second, then the circumference, the distance around, is changing by 12.5 centimeters per second. Seems like something that wouldn't really help you. Why do you care how fast the circumference of a circle changes? Right? But it's just a start to kind of understand how these things work. You're going to have some formula either given to you, described in the problem, or you'll have to set it up. But you're going to have some formula that relates the two variables together. You're then just going to take an implicit derivative, right? Divide everything by dt, and then plug in what you know. Solve for the one that you don't know. Okay. Let's try another one here. Slightly more real example, though, still a little further off. So water's poured onto a surface, so that a puddle forms to a circle, right? So you're just dumping something out, and the liquid is making a circle. Okay, that's not too far unbelievable. The chances of making a perfect circle, slim, but you can imagine that it's an ideal case. If the area of the puddle is changing by 10 centimeters squared per second, so we know how fast the area is changing. And immediately we can look at this, and we know that it's the change in area over the change in time, which is how fast the area is changing over time. That's going to be that number. And we know it's changing by 10 centimeters squared per second whenever the radius is 3 centimeters. So the change in that area depends on what the radius is. Okay. So in other words, a smaller circle, as it extends, you see the area go faster than you would if the circle is already larger and you're extending it more. So what we need is we need a formula that relates the area of a circle to the radius. So what's the area of a circle? I think you're on the right track. Just like we did with the circumference. That's okay. So the circumference 2 pi times the radius. The area pi times the radius squared. Does that make sense? Okay. All right, so just like we did before, this is our equation that's going to relate the two, relate the area to the radius, right, just the area of the circle. So we're going to take the implicit derivative, and I'm just going to go to the next page. We'll come back to that. If we take the implicit derivative, we're going to get 1 times dA is equal to pi times 2r dr. Derivative of r squared is 2r. And then we get the dr. Divide both sides by dt. And what we get is dA over dt. Is equal to 2 pi r times dr over dt. What we're looking for, how fast is the radius changing? We know how fast the area is changing. So what we need to do is we need to solve for dr over dt. We want this part by itself. So you can solve it now and then plug in the numbers, or you can plug in the numbers and then solve it, whatever you're most comfortable with. But we know that area, or the change in area over time, is 10 centimeters squared per second, and that's equal to 2 pi times the radius, which was just 3 centimeters. That's given to us in the problem. Times dr over dt, which is what we're looking for. And so to solve for dr over dt, we just take 10 and basically divide by 6 pi. And you should get that the radius is changing by about half a centimeter per second. Did y'all get that? Are you divided? 10 divided by 6 pi? Yeah. Yeah, so 2 times 3 is 6, right? So.
Yeah, is your units equal to squared, the centimeters?
No, that's just your units, right? So, well, okay. You bring about a really, really good point there, something that you almost never talk about in a calculus class. And since we kind of got time, I'll show you what happens here. So when you're dealing with units in a problem like this, it's just like dealing with variables. They act the same. As in how you can cancel them out and things like that. So what we had was 10 centimeters squared per second. That was in the numerator. Divided by, it was 2 pi times 3 seconds. When we divide the two, we've got centimeters squared in the numerator, centimeters in the denominator. We basically, yeah, they act just like a variable. So they just kind of cancel each other out. And you're left with just, you know, whatever the number is, 0.53 centimeters per second.
Yeah, try putting in 6 pi, but you need 5 something, but I get 6 pi just for actual answer for 6 pi.
Yeah.
Again,
Okay.
is it that the 6 pi?
Put 10 over 6 pi parentheses. It does 10 over 6, then multiplies by pi. Yeah. If you do it that way. But yeah, so units just act like variables, right? So you can cancel them out in the same way. You can also kind of just think about it like if an area is changing, area is always in units squared, right? So if an area is changing, then it'll be units squared per second, or per minute, depending on what the units are. If it's a volume that's changing, it's going to be distance cubed per second. If it's a distance that's changing, then it's just the units, the first power. So now we're going to go back to essentially this formula where we're talking about at the very beginning. We've got a basketball that's being inflated so that the radius changes by 8 centimeters per second whenever the radius is 5 centimeters. And so as this thing's being inflated, when the radius reaches 5 centimeters, the radius is changing by 8 centimeters per second. So it's inflating really, really quickly. So we want to know how fast the volume is changing at this time. Well, just like we did before, we need some kind of formula to relate the two. In this case, it's the volume of a sphere. But now the steps are all the same. Take the implicit derivative, plug in what we know. Okay? We'll take the implicit derivative, divide by dt, and then plug it. So just go into the next page again. 4/3 pi r cubed. And so if we take the implicit derivative, we're going to get 1 times dv is equal to 4/3 pi times 3r squared dr. If we simplify some things, we can kind of just cancel out these 3's. And you're left with dv is equal to 4 pi r squared times dr. Divide both sides by dt. And now we want to know how fast the volume is changing. We've got that by itself over here. So we can just plug everything in. 4 pi, we know the radius. And this is where you have to be careful about which one's the radius and which one's the rate of change of the radius. Okay. So in this case, you're looking for a rate. This is dr over dt. That's how fast the radius is changing. And then this is just r. And so what we get is 5 centimeters squared times 8 centimeters per second. So the rate of change of the volume, 800 pi, whatever that is. That's pretty quick. 25 times 4 is 100, times 8 is 800, times pi. Yeah. Multiply it all up. We're going to get a decimal. Yeah, times 8 times 5. We'll just stick with that. That's a lot. Okay, so what would the units be? That's it. Centimeters cubed per second. Volume is a measurement of cubic distance. That's a bad way to say that. Volume is always in distance cubed. Area is always in distance squared. And the distance is just distance. So about 2,500 centimeters or cubic centimeters per second. I would say inflating a basketball, that would inflate the basketball probably in less than a second. I'm not sure of the volume of a general basketball, but that sounds like I made the numbers way too big for me. Okay. Let's try another example that's very, very similar to this one, but it's probably one of my favorite problems to do. And I'm going to try to change it up a little bit so that we have to do more than one thing with it, which I hope you'll see. Let's see. Give me a minute to write this down. Oh man, I ran out of space on that. Okay. I just wanted to write it all down so that it would be there. I could have just said it in words, but I wanted to write it all down so you don't reference back to it. So, you're standing at the bottom of a volcano, or at least close enough to a volcano where you're about 5,000 kilometers from it. I know that's a ways, but if you think about mountains, it may not be quite as far as you think when you're talking about that. I understand it seems a little exaggerated, and it is. Okay? It's not exactly the case. But if you ever watched anything about the volcano movies, or if you ever seen the movie Dante's Peak, right, there's a really good really good scene of this in that movie, and that's what I always think of when I think of the problem. But when a volcano erupts, it ejects this huge cloud of ash and dust, right? And if it's a really violent eruption, that cloud will travel down essentially the side of the volcano. That's what this is, okay? You don't need to know what that is. I just wrote that in there because I know what the word is. Anyway, it's a steaming hot cloud of ashes and burning flame. You don't want to be there when it gets there, okay? So you see this eruption, and you can tell that once the clouds moved 100 kilometers down the slope, right, it's now traveling at about 200 kilometers per second. So you're going to assume that it can't, it's not, well, okay. You want to assume that when it erupts in a hemispherical shape, right? So instead of a sphere, like you would think of like a basketball, it's a hemisphere. So it starts at one point and then it's essentially going outwards like that, okay? It's spreading out like that in all directions. So the volume of a sphere is 4/3 pi r cubed. The volume of a hemisphere is half of that, so 2/3 pi r cubed. On a test, if I asked you to do something that was not a basic formula, I would give it to you. I didn't do it like I wanted to. I changed it. All right, okay. Hang on. That's the part we're trying to figure out. Okay. Now it's more like what I want to do. And this is actually not too far off as far as the expansion rate of that volcano. But you gotta think it's going in all directions too. So we can tell once that it's moved 100 kilometers that the volume is changing by that amount. We want to figure out the change in the radius. That's what we're doing. And so we know we're 5,000 kilometers away. We're going to use this last. We know the change in volume. And we know the radius when it reaches, when that volume is changing at that rate. And so let's go back to our formula. Just like we did before, we're going to take the implicit derivative. 1 dV, 2/3 pi, 3 r squared dr. Again, the 3's will cancel. You're left with dV is equal to 2 pi r squared times dr. Divide both sides by dt. So we're trying to figure out how much time we have to get away. And we know how the volume is changing. I know I changed that from the original problem. We know now how the volume is changing. We know the radius when the volume is changing that much. If we can figure out how fast the radius is changing, that's essentially, you're standing somewhere close to that volcano. That's going to tell you the linear velocity, how fast it's coming at you. And then you can take that and determine from your distance how much time you have to get away before it gets to you. So, the change in volume was 1,500 kilometers cubed per second. Maybe more of a per minute kind of thing than per second. That sounds like a lot per second. But we'll go with it. Okay. 2 pi. At this point, the radius is 100 kilometers squared. And we're just looking for the change in radius over the change in time. Right? How fast is the radius changing? We know that, then we can figure out how fast it's going to travel that 5,000 kilometers. solve this for dr over dt, you should get that the radius is changing at a rate of 0.024 kilometers per second. Not bad. That's not that bad. It's 24 meters a second. 24 meters per second. Being 5,000 kilometers away, you'd actually probably never see this eruption. So just to make it a little bit more reasonable, with that original problem, let's just say you're 500 kilometers from it. That makes it a little more perilous. Now we actually have to worry about it getting to us at some point. So at 500 kilometers, and we can actually do both. We can do 500 and 5,000. We know that the radius is changing by this much. And so if you're 500 kilometers from where that eruption occurs, and you know that it's traveling towards you at 0.024 kilometers per second, to figure out the amount of time, we know the change in radius so 500 kilometers, and we know the rate is 0.024 kilometers per second. This is essentially our linear velocity, if you think about it, where you're standing and something's coming towards you. Okay, so that's speed. Speed is always equal to distance over time. We're looking for time. And so we want to find time, just rearranging this equation. That's the distance divided by the velocity, which is 500 kilometers divided by kilometers per second. 20,833. Divide that by 60. What do you get? Okay, divide it by 60 again. That's reasonable. And about 6 hours to get away. If you're 500 kilometers. If you're 5,000 kilometers, it'd be 10 times this, right? And then it makes it, now you got probably pretty much a whole day to escape. The expansion rate of that volcano that I changed it to, when I changed the volume, that's actually, if I remember correctly, not too far off from how fast these things usually erupt. I know I've used that number before on many tests. That's usually that's the volume ejected in a certain amount of time. It could be in terms of minutes and not seconds, which would very much change our answer, but I'm not positive on that. It doesn't really matter. As you can see, you can still figure it out. Figure out how much time you have. If you can determine, well, you didn't have to determine the speed, we figured it out. Okay. But this is a good problem, it's a good type of problem. It kind of shows you what you can do with this stuff. So not only can you figure out how fast it was expanding, or how fast the radius is changing, you can then take that information and determine how to save yourself from this volcano. Right. Let's see. Let's do one or two more. You guys, does this make sense? Autumn, you kind of with me on this? Is this okay? Yeah. Okay. I'm sure questions will arise. So And I'm sure I'll have to do this again for the other folks. And that's okay, because I actually like this one. I'll get more real numbers and know exactly what those numbers are, so we can figure out what we're really doing. In some cases, minutes would be what you would have instead of hours. But it seems like that wasn't so bad. Let's do one more example of something that you kind of have to set up a little differently, and then I think for the two of you that'll be enough for today. And we'll do this again on Wednesday, and we'll just work some more problems. Monday we'll review for the test, and then next Wednesday we'll do. Okay. So we got a 13-foot ladder leaning against the side of a house, and the bottom starts to kind of slide away from it. And so by the time that the base has slided 12 feet away from the house, right, it's moving at a rate of 5 feet per second. And so we want to figure out how fast is the top of the ladder sliding down the house, right? So, and there's a picture in the book. But what you've got here is you've got a ladder that makes some angle with the side of a house. This part of the ladder is moving that way, and so the top part is moving down because that thing has to stay at 13 feet, right? It's a ladder. You can't change how long it is, right? So it's not stretching and shrinking. It's just sliding down. There's one piece. This piece starts to move this way, which forces the end to go that way. And so we know that when this distance is 12 feet, this rate is changing by 5 feet per second. We want to know how fast this distance is changing. We'll call that dy. We want to know how fast it's dropping down the wall. The hard part about this problem is not solving it necessarily, but figuring out how do we want to set it up. How do these things relate to each other? Right? How can we relate this side, where it's sliding, to this side, and to the other side? Is there any formulas that pop out of your head? Anything having to do with essentially a right triangle? Well, okay. Now I've got the angle drawn here, and you can probably do this in terms of angles. But I think we might be able to do it in an easier way without the angle. Now I think it asks later how fast it's moving. Yeah, so the first one's just how fast the top of the ladder sliding down. It's all we'll probably do. The other two is at what rate is the area of the triangle formed by the ladder changing. And then the third one is at what rate is the angle changing. I don't think we need, well, we can determine all that stuff, but we would have to set a different formula for recovery. We don't need all that to figure out how fast the edge is coming down. So let's not worry. We could use the angle, but I don't think we need to, right? Is there another formula that relates sides of a right triangle to each other? Guy named Pythagoras?
Yeah, it's back
Right.
here.
There you go. A squared plus b squared is equal to c squared. There's our formula. And pretty much, if you're looking for something that occurs on the side of a right triangle, Pythagorean theorem's about where you want to start. Right? If we were dealing with the angle, we would deal with trig functions. But if we're dealing with the sides, then let's just deal with Pythagorean theorem. So, just to make this more reasonable, and just so our letters kind of match up, I'm going to call this x, this is z, and this is y. Okay, those are the sides of the triangle. So instead of x, a squared plus b squared equals c squared, we have x squared plus y squared equals z squared. Same exact formula. I'm just trying to make the letters match up. And so let's take this to the next slide. And just starting with our formula, we're going to do what we've been doing all day so far. Take the derivative implicitly, divide everything by dt. And so the derivative of x squared is just 2x dx. The derivative of y squared is 2y dy. Derivative of z squared is 2z dz. Divide everything by dt. And so what we get is 2x. Notice one other thing we could do here. They've all got 2's in them. So we can essentially divide everything by 2 and just get rid of those 2's. That'll save us a little bit of trouble. Just dealing with constants. And so we get x times dx over dt plus y times dy over dt is equal to z times dz over dt. Well, what do we know here? When we're talking about x, we're talking about the bottom of the triangle. And so we know that x, the distance, is just going to be 12 feet. And dx over dt, the rate of change, is 5 feet per second. And so we know that x is 12 feet. And dx over dt is 5 feet per second. Plus. Okay. Now, y is the thing we're dealing with, so we'll come back to that in just a second. If we look at z, which is our hypotenuse, z is 13. Now here's my question. How fast is the hypotenuse changing? Or does the hypotenuse change at all? Remember that hypotenuse of this triangle is our ladder. This thing is constrained to be 13 feet no matter what. You can't shorten it. It's not going to shorten itself, right? It's just a regular one-piece ladder that starts sliding off the house. Okay? So the hypotenuse doesn't change, which means dz over dt would be what? Close? 0. There's no change. No change means 0. Okay? And I'll explain to you why this should make sense in just a minute when we're done. As to why this shouldn't matter as to the entirety of the problem. Now we're left with y and dy over dt. dy over dt, the rate of change is what we're looking for. But we don't know what y is. We don't know what the height is. Right? What's the height of this side of the triangle? But we can figure that out by just using the Pythagorean theorem in the first place. We know x is 12, z is 13. If we want this edge of the triangle, we want just y. Then we get 12 squared plus y squared is equal to 13 squared. And subtract 144, you get 25. Take the square root, and you see that y is 5. It's a special triangle, but you got 12 and 13 is one, or 12 is one side, 13 is the hypotenuse, 5 is always the other side. If you got 5 is one side and 13 is the hypotenuse, then 12 is the other side. So we know that y is 5. This distance is just 5 feet from the ground. Right? But it's falling. It's going down. And so let's go. We know y is now 5 feet. And we're looking for dy over dt. So now we just have to solve all this stuff. The right-hand side goes to 0. 5 times 12 is 60. And so we move that to the other side. You should kind of be able to see what the answer is going to be at this point. You get 60 feet squared per second. And I'm just plus 5 with dy over dt is equal to 0. We move this across, we get 5 feet times dy over dt equal to negative 60. And I'm just kind of keeping the units on there even though we don't really need it. Divide by 5. Or divide by 5 feet. And you get the ladder's falling at 12 feet per second, which seems reasonable. Now, if we go back and just look at the original picture, right, remember the hypotenuse part is the ladder, it's the constrained part. So if you start to pull a ladder from this side, right, you're just pulling it out, obviously this side is going to drop, right, but it has nothing to do with how long the ladder is. Right? If the ladder was shorter and it was here, you pulling it is still going to affect it in a very similar way. It wouldn't be exactly the same. Right? So the rate at which you pull it out is the only thing that really matters. The rate and its distance. Right? Otherwise, the length of that ladder doesn't matter at all. Now when you're trying to calculate the rate, it only matters when you're trying to calculate where the other side is. Right? Because you want to know where it meets the wall here, you need to know the hypotenuse for that. But when you're trying to determine how fast it's actually falling, it doesn't have anything to do with the hypotenuse. It has to do with how fast the other end is moving. Does that make sense? There's another problem which we'll probably do on Wednesday. Yeah. Another problem we'll probably do on Wednesday that has to do, very similar to this, but has to do with speeding cars and how fast they separate from each other. Things like that. Plenty more examples we can do, but since half of you were here, we'll go ahead and stop for today and pick back up on Wednesday. What's that? Yeah, it should be similar to this. Should be similar to this one. You're going to see one or two that have to do with angles. We didn't talk about that yet. We'll do that next time. I know trig functions tend to give people the most trouble, so I'm going to say that one. Everybody can hear what I have to say. Even though the video might help, I would hope, but just in case. It's easier when you can ask questions. So you can try these for now. If they give you too much trouble, bring questions to class. We'll work them in class because these are the kind of things that no problem is similar, right? Everything can be set up a different way. Like even on this one, we could have set it up differently to still get the same answer, depending on if we use the trig functions or not. We could probably take that answer and determine how fast that angle is changing and that kind of thing, with very little complexity. And maybe we'll do that next time too. So the plan, go back over related rates on Wednesday. On Monday, we'll review. And then on Wednesday, you'll have a test. So you'll have a quiz Wednesday and Monday. One Monday, I'll probably do like I've done before and put it on the internet, on Canvas. That way it's kind of like a test review. And then we'll have a test on Wednesday. Questions you have? Issues? Concerns? Okay, so I'm going to, I'll upload this video and the notes. I have no idea what the video, I mean, you're going to hear everything I said, everything you guys said. I'm not going to bother trying to edit it for simplicity's sake, but this way at least you guys have it.